In this part of the lecture, uh, we will see something more about the inertia tensor. In our previous part of the lecture, we had seen that the inertia tensor of the body B with respect to the center of mass expressed in the frame 0 is given by this matrix here, which is a 3 by 3 matrix, and one can see that it is a symmetric matrix. The diagonal elements are here, they are the moments of inertia, and the off diagonal elements, you can see that it's a symmetric matrix. So this element is the same as this is the same as this, and this element is the same as this element. You can also see that the diagonal elements are positive. So the inertia tensor is symmetric with real elements. All the elements of this matrix are real. All the diagonal elements, that is the moments of inertia, are always positive. This we have already seen. The sum of the moments of inertia is always constant, irrespective of the orientation of the frame of expression. And this is a matrix property. You can see that the sum of the diagonal elements remains invariant. And even if you change the orientation of the frame of expression, you will still obtain the same sum. It's called as a trace. The inertia tensor is a positive definite matrix. That is, this product x transpose I x, this works out to be a scalar because I, the inertia tensor, is a 3 by 3 matrix and x vector is a 3 by 1. So here when you have x transpose, it's a 1 by 3. So the resultant is a scalar in the numerator and also a scalar in the denominator. So this term should be greater than 0. It means that it is positive definite. Consecutively, its eigenvalues are always positive real. So this automatically implies that the eigenvalues for this I metric, for this inertia tensor, are always positive real. For a rigid body continuum, the elements can be expressed as limits of sums. So these elements of this inertia tensor can be expressed as limits of sums, amounting to integrals over the volume of the body, just like this. So this summation symbol, when it is expressed as the limit of a sum, so this uh, it becomes an integral over the continuum. So here you have the various distances, but they are with respect, they are the coordinates, they are the coordinates of the position vector from the center of mass. Rho is a density, dx, dy, dz, these are the elemental lengths along the chosen axis. So this is for a rigid body continuum. The inertia tensor of the rigid body about its center of mass C, expressed in the body frame B, is related to the inertia tensor expressed in the inertial frame 0 as IB with respect to C expressed in 0 is equal to R B to 0, IB with respect to C expressed in the frame B was multiplied by R B to 0 transpose. If the frame B is fixed on the rigid body, if this is aligned along the principal directions, one can choose the frame B and fix it on the rigid body. The orientation of the frame B, if it is so chosen that the off diagonal elements or the products of inertia, they become zero, and you're left only with the diagonal elements, which are the moments of inertia. Then how can the orientation of the frame B be determined with respect to the frame 0? This is the question before us. Let's say that the inertia tensor uh, for the frame B, it appears like this, just as we have mentioned here. The moments of inertia correspond to the diagonal terms, and the off diagonal terms are 0. So this equation which we have here, we can write it like this: I B with respect to C expressed in frame 0, RB to 0 is equal to RB to 0, I B with respect to C expressed in the frame B. If we elaborate on R, it can be broken into 3 columns. The ith column, that is the I B expressed in the frame 0, JB expressed in the frame 0, and KB expressed in the frame 0. So if we write it like this, you can see that I into this R matrix written in this form is equal to the R matrix written in this form operating on the diagonalized inertia tensor, which is expressed in the frame B. So this becomes, if we just multiply this column by column, you can see, if we just write the columns of this product, you can see I B with respect to C expressed in the frame 0 operating on the first column. That corresponds to lambda 1 operating on IB expressed in the frame C. Likewise, IB with respect to C expressed in the frame 0 operating on J, the unit vector J of the frame B expressed in the frame 0 is equal to lambda 2 JB expressed in the frame 0, and same way for the third column, which is here. So in general, we can write this as the inertia tensor operating on a unit vector is equal to a scalar lambda corresponding to that unit vector, the same direction, operating on the unit vector. So x cap can take any one of these forms here. So in general, we write it like this. Now, x cap is a unit vector along one of the principal directions. For the above equation to have a non-trivial solution, the determinant of lambda x multiplied by the unit matrix minus the inertia tensor of the body with respect to center of mass expressed in frame 0, this should be equal to 0. So this is actually a characteristic equation. The above equation is an eigenvalue problem. The equation which we write here, this, it indicates an eigenvalue problem, and x cap is the eigenvector corresponding to the eigenvalue lambda x. So x cap is just indicating, it's a unit vector indicating the direction along which this occurs, and it corresponds to the eigenvalue lambda x. The eigenvalues are the roots of the characteristic polynomial. So lambda I minus lambda minus IB with respect to C expressed in the frame 0. So this is a characteristic polynomial. Now, how are the eigenvalues of the inertia tensor of the rigid body about its center of mass, but expressed in different frames, frame 0 or frame B? How are they related to each other? Let's start with the characteristic polynomial. Lambda I, this determinant, lambda I minus IB with respect to C expressed in the frame 0. And we we bring in the inertia tensor. We express this inertia tensor, which was earlier expressed in the frame 0. We express it in terms of the frame B. So we just replace this with this. And here we have the same lambda into I. We can write this unit matrix as R B to 0, I R B to 0 transpose minus this part is exactly the same over here. And here lambda is a scalar, so we just take it, we take R B to 0 common on the left side and R B to 0 transpose common on the right side. And we have the we take the determinant for each because we can write this as a product of these three determinants. And this can be written as lambda I minus I B with respect to C expressed in the frame B. And this is because each of these determinants R B to 0 and determinant R B to 0 transpose, they become equal to 1. This is based on the properties of the R matrix, which we have already seen earlier. Hence, the eigenvalues of the inertia tensor of the rigid body about its center of mass are independent of the frame of expression.